Hi, welcome to Math Club Meeting 14. I'm Eleanor and I'm so excited today to solve 4 very interesting math problems with you. Let's get started. Firstly, question 1. In the diagram, PQ is the diameter of a circular base of the cylinder. RS is the diameter of the top base of the cylinder and is directly above PQ as shown. Point U is on the circumference of the top face, halfway between R and S. Point T is on the cylinder and is directly above P. So suppose that QS is equal to M, PT is equal to N, and this just means that M and N are both greater than 1 and N is smaller than M. If QU is equal to 9 root 33 and UT is equal to 40, what is the remainder when the integer is equal to QT squared and is divided by 100? So if you have already done this problem, I'm so proud of you and I'm excited to solve it with you. If you haven't solved this problem yet, feel free to pause this video and come back when you have a solution. Let's start solving the question. So now I have labeled UT to be having a length of 40 and Q has a length of 9 root 33. So now let's observe our diagram. So we should actually observe that since it's a cylinder and RS is actually directly above PQ. So R and P is connecting these two lines. So RP should be perpendicular to PQ. So let's draw our triangle. We have P, should be a bit longer, PQ, and it's T, so we have N. And if we let the radius of the circle equal to R, PQ is the diameter, so this one should be 2R. And now we can use Pythagorean theorem. It's basically a theorem for right angle triangles. A squared plus B squared is equal to C squared. So QT squared is equal to N squared plus 4R squared. So QT is the square root of this. So now basically we just need to find out what is N and what is R, which will enable us to solve for QT. Let's start applying our knowledge. So in this scenario, since it's a right cylinder, we know that the top surface is perpendicular to its height. So any line on the top surface is perpendicular to the height, which is just PR or TR. So TRU is a right triangle, and this is also the same for Q, S, and U. So we can come up with the equations that TR squared plus RU squared is equal to TU squared. And similarly, QS squared plus US squared is equal to UQ squared. And now we want to try to find what is RU and SU. So let's draw the top surface of the cylinder. So the top surface of a cylinder is a circle. Obviously, it's not a very good representation of a circle, but you get the idea. So there's R, there's S, there's U. So now we can just connect them. It's not drawn to scale, unfortunately. So let's just let the center be O. So we know that O is R, RS is also R, and we can just connect U to O. So this is R as well. So by the Pythagorean theorem, thank you Pythagoras, we know that RU is actually equal to the square root of 2R, which is also the same for this one. So we can just substitute this into our equation above. So we have 2R squared plus RT squared is equal to TU squared, which is also 40 squared. And we also have 2R squared plus M squared is equal to 9 square root of 33 squared, which is just equal to 2,673. Then we can just go back to the figure and we can find out that RT is essentially M minus N. So we can since RT is equal to m minus n, we know that we can just replace RT by 2r squared plus m minus n squared is equal to 1,600. So we can just simplify into 2r squared plus two m minus n is equal to 1,600. And from this equation, we can just carry it over to r squared plus m squared is equal to 2. Then since we have a system of equations, let this be equation 1 and this be equation 2. We can just do equation 1 minus equation 2. So we have m squared plus 2r squared minus, let's copy down the whole thing, and it's equal to 1,073. M squared plus 2r squared. So now we can cancel a lot of terms, which simplifies the expression m squared minus m squared. So this will simplify into 2mn plus n squared is equal to 1,073. So we can actually factor out the n because it's a common variable. So it's n minus 2m times n equal to 1,073. So while this equation might seem daunting and you might be overwhelmed because there's no way you can factor this, but we can actually use a trick. So let's find the factors of 1,073. So there's 1 times 1,073. But if you do enough trial and error, or if you actually happen to memorize it, it's actually 29 plus 37. So we know that n times 2m minus n is equal to 1,037. So n times 2m minus n can also be equal to 29 times 37, or it can be equal to 1 times 1,073, sorry. So here's a list containing all the possible values of n and 2m minus n. However, recall that in the question there is a constraint that n must be smaller than m. So we need to find a way to verify that m is smaller than n. So firstly, we remember that we have derived that this is equal to 1,073. So 2m minus n is equal to 1,073 divided by n. So 2m is equal to 1,073 divided by m plus n. And this is just equal to 2m minus n. So it's 2m minus n plus n is equal to 2m. So m is just a half of all of this, 2m minus n plus n. Okay, so now we can start calculating for m. For example, in our first scenario, n is equal to 1, 2m minus n is equal to 1,073. So m would be equal to a half times 173 plus 1, which is equal to 537. So this would be 537, 33, 33, and 537. So when we want to check the condition that n must be smaller than m, we see that this case does not work because 1,073 is greater than 557. So this one does not work as well. Now we have to figure out whether n is equal to 1 or is it equal to 29. So in the diagram, we know that QU is larger than QS. So QU is equal to 933 and QS is just equal to m. This means that m needs to be smaller than 9 root 33, which is just around 51.7. So this means that m cannot be equal to 537, otherwise it won't fulfill this requirement. So this means that we have reached the conclusion that n is equal to 29, m is equal to 33. We have previously determined that qt squared is equal to n squared plus 4r squared. So now we just have to solve for r. We're just one step away from our answer. Since we have derived that m minus n squared plus 2r squared is equal to 1,600. So we know that the m is minus n is just 4 squared plus 2r squared is 1,600. So 2r squared is just 1584. Now let's solve the final question. Qt squared is equal to n squared plus 4r squared, which is just, this one is just 2 times 2r squared, which is equal to 841 plus 3168, which is equal to 4009. And the remainder when 4009 divided by 100 is 9. So let's solve question 2 together. A cube with vertices F, G, H, J, K, L, M, N has the edge length of 200. Point P on HG is as shown. The shortest distance from G to a point inside the triangle PFM is 100. So which of the following is closest to the length of HP? So first of all, let's just let HP equal to X. And because a cube is basically like a square on 6 sides, so each side has a length of 200. So HG is equal to 200, so PG is just 200 minus X. So an easy way to tackle this problem is to consider the triangular base pyramid F, G, M, and P, and to calculate its volume in 2 different ways set to equal, and then solve for X. Let's calculate the volume of F, P, M, G when F, M, G is the base. Okay, so firstly we have 1/3 times the area of the base, which is a triangle. So 1/2 times the base times the height times PG, which is X. So the area is 1/3 times 20,000 times X. Then we can consider the tetrahedron to have the base of F. Oops, that was a terrible drawing. F, P, and M as the base. So the height will be the perpendicular extension of G to the triangle. And this length is actually equal to 100 because the perpendicular distance from G to the triangle FP of M is actually equal to the shortest distance, which is 100. So the height is 100. And now we would like to find the area of the base, which is F, P, and M. So since FMG is a right angle triangle, okay, let's draw FPM. FP and M. Since this is a right angle triangle, this is 200, this is 200. So this one is equal to 200 square root 2. And then we can calculate it with the Pythagorean theorem to find FP, because we know that FG is equal to 200 and this one is equal to X. So this one is X squared plus 40,000 square root. So this is FP. And since it's an isosceles triangle, MP is also equal to this. So if we let T be the midpoint of F and M, we know that FT is equal to MT, which is 100 square root of 2. So by the Pythagorean theorem, PT squared is equal to FP squared minus FT squared. So FP squared is just X squared plus 40 20,000. And ft squared is just 100 square root 2 squared, so it's 20,000. So we know that pt is equal to the square root of x squared plus 20,000. So then we can find the area of triangle FMP, which is equal to a half times the base FM, 200 square root of 2, times PT, x squared plus 20,000. Oops, one more zero. So then we can just calculate the volume is equal to a third times the area times the height, which is just over here. It's equal to the shortest distance, which is equal to 100. Good job, everyone, for solving the question up to this one. Now, since the volume of this tetrahedron is the same, we can say that this expression on the top is equal to this expression. So now let's set the equation to set them to be equal. This one is equal to this equation. X. And we see that 1 over 3 appears on both sides, so we can just cancel it out. And then we can try to cancel out other terms as well. So now, let's see, what can we cancel? This thing is equal to 100 times 200. So this thing can be canceled out. So now we are left with x equal to 1 over 2 times square root of 2 times x squared plus 20,000. I'll have to be careful and write neatly to prevent careless mistakes, because those can be very painful. 2x is equal to square root of 2 times x squared plus 20,000. Now let's just square both sides to get rid of the square roots so our calculations are easier. 4x squared is equal to 2 times this. So now we can just distribute the 2 to each of the things inside, equal to 2x squared plus 40,000. 2x squared is equal to 40,000. So now x squared is equal to 20,000. So let's just take the square root of this, and it's equal to 100 square root 2. Because we know that x is a length, so it must be greater than 0. So it can't be negative 100 and square root 2. It has to be positive. So because the question is asking for HP, HP is equal to 200 minus x, which is equal to 200 minus 100 square root 2, which is around 58.58. So the closest integer of 58.58 is actually 59. So the answer is 50. Now moving on to question 3. So in this question, Roberta chooses an integer from the set, an integer r from the set 2, 3, 4, 5, 6, 7, 8, 9, an integer s from the other set, and an integer t from the other set. How much possible values are there for the product r, s, and t? Okay, so firstly, let's identify if there's anything interesting or useful that may help us in the set. Firstly, the first set is just 2, 3, 4, 5, 6, 7, 8, 9. It's just some integers that are of single digit. But things start to get interesting in the second set. We have 22, and we know that 22 is just equals to 2 times 11. And 33 is 3 times 11, and so on. 44 is 4 times 11. 55 is 5 times 11, and at last, at 99, it's 9 times 11. Okay, now for our third set, we can actually find a similar pattern as well. 202 is just 2 times 101. 303 is just 3 times 101, and so on. We have 9 times 101. Okay, now the question wants us to find possible values of the products R, S, and T. But we can express S as 11 times, let's say, a number M. And M is just a number from 2 to 9. And similarly, we can express T as 101 times N. So we can deduce that R S T is just equal to R, which is the same, times 11M times 101 N, which is just, we can just take out the numbers because they're constants. Oops. Since 11 and 101 are all primes, and they're present in each of the product RST, it means that the number of possible values for RST is the same as the number of values for R, M, and N. So we just need to find the number of possible values for R, M, and N if we want to find the number of possible values for R, S, and T. So now we can analyze our sets. So we should just do the analysis on the factors to count the number of total values of R and M and N. Otherwise, it will be too tedious to list out each of the calculations. And when analyzing the variables, we can see that 5 is a prime number. Well, okay, 2, 3, 5, and 7 are prime numbers. And we want to make our life simpler, so we should just pick 2 of the prime numbers. But notice that 2 can be also shown in 2 is also in the factor 2 is also in 4 and 8. Similarly, the factor 3 is also in 6 and 9. So to make our calculation simpler, we will make the decision of choosing 5 and 7 to do analysis. Okay, so we notice that in this set, there can be only one multiple of 5 and one multiple of 7, which is also same in this one and this one. So we know that in RMN, at most, there can be 3 factors of 5 at most, and similarly, 3 factors of 7 max. So now we can just count the number of possible values for R, M, and N by considering the different possibilities for the number of factors 5 and 7. So let's use the value y. Let's use y be equal to the number of factors of 5, and let z be equal to the number of factors of 7. So we know that there can be different combinations. Firstly, and also since there we can only choose one number from this set, one number from the second set, and one number from the third set, there can be 3 factors of 5 or 7 at most. So we know that y plus z is smaller than or equal to 3. So now let's consider the different scenarios. Firstly, we can have y is equal to 3. So there are all of the factors chosen from the sets are 5, or we can have z is equal to 3 when all of the factors from the set chosen are 3. We can also have y equals to 2, z equals to 1. Similarly, when y is equal to 1, z is equal to 2. Or y is equal to 2. And yeah, it just means that there will be 2 factors of 5, 0 factors of 7. And we can also use symmetry to deduce that y is equal to 0. This is also a possible value. So these are all the possible values. So in the following, I will be guiding you on how to count the number of possible values for RMN for each of all of these different conditions, which will be a lot. So we can just draw a table so we can record these values. Okay, I'm so excited. Let's start. Firstly, case 1. When y is equal to 3, meaning that there are 3 factors of 5. This means that r is equal to m is equal to n, which is equal to 5. Rmn will be equal to 5 squared. And since when y is equal to 3, it means that we have 3 factors of 5. So r, m, and n must be equal to 5. So it means that there is only one possible value. And similarly, case 2, when g is equal to 3, r equals to m equals to n equals to 7. And since we can only choose one number from each set, there's only one possible value as well. So let's record these in the table to keep organized. 1 and 1. Great. Now we have the other cases. We have case 3 when y is equal to 2, z is equal to 1. This means that two of the r and m is equal to 5. The other one is equal to 7. So Rmn must equal to 5 squared times 7. Because that's the only choice we have if we want to fulfill the requirements of having 2 factors of 5 and 1 factor of 7. So there's only one possibility for this case. Next we have case 4, which is very similar to case 3 when we have 1 factor of 5 and 2 factors of 7. So this is only one case. And let's write that down. Okay, great. Now we can move on to the 5th case. When y is equal to 2 and z is equal to 0, it means that 2 of r, m, or n is equal to 5. And the third cannot be equal to 5 or 7. Otherwise, if the third one was 5, y would be equal to 3. Or if the third one was equal to 7, then z would be equal to 1. So it does not fulfill the requirements. And recall that the set is from 2, 3, 4, 5, 6, 7, 8, and 9. But it cannot be equal to 5, or it cannot be equal to 7. So we only have 6 possibilities for the third number. And the 2 numbers are equal to 5. So possible values of Rmn can include 5 squared times 2, or we have 5 squared times 4. So in conclusion, there are 6 different values for this case. Then we have case 6 when y is equal to 0 and z is equal to 2. So we can apply the same logic for this question. 2 of them will be equal to 7. The third one cannot be equal to 5. The third number cannot be equal to 5 or 7. So we also have 6 possibilities for this one. So similarly, in case 6, there are 6 possible answers. Let's record that in our table. 6 and 6. Okay, now we have another case. Case 7. When y is equal to 1 and z is equal to 1. This is quite similar to the cases 5 and 6. So one of the number, the first number is supposed to be 7. The second number is fixed. The second factor is 5. So we have 6 more choices for the third number. It can be a part of this. There are 6 possibilities over here. So there are 6 possibilities. And here there's only one possibility. So for case 7, there's a total of 6 values for R, M, and N. Okay, let's continue on to the next case. So the cases are now starting to become a bit more complex. Case 8, we have y is equal to 1, z is equal to 0. So firstly, one number is equal to 5. And let's just suppose r is 5 for simplicity, because the order of the numbers do not matter. We only are concerned about their results. So now, and m and n cannot be equal to 5 or 7. So each of m and n must be equal to 2, 3, 4, 6, 8, and 9. So, however, we need to make sure that we are not overcounting it. For example, when m is equal to, so now this is a counter example. So we can't just simply multiply 6 by 6 because we will be overcounting. For example, when we have m is equal to 4, n is equal to 6, mn will be equal to 24. But m can also be 3 and n can be 8, so mn will be equal to 24 as well. This is a reason why we can't just multiply 6 times 6, because we will be overcounting. So a simple foolproof method is to just set up a table of values. 2, 3, 4, 6, 8, 9. So to save time, I've already filled in the table of values, and after counting, we can find out that there's actually only 16 distinct pairs when we multiply m by n. Hence, there's only 16 possible values for m times n, and because r is fixed, we know that there can only be 16 possible values for r and n when y is equal to 1 and z is equal to 0. So let's write that down. Okay, now we have case, what case is it again? Okay, case 9, great. Case 9 is when y is equal to 0 and z is equal to 1. So we can actually apply the same logic of case 8. Let's just say that r is equal to 7, and we can just set up the same table of values, and because we know that m and n cannot be equal to 5 or 7. So according to the same logic, there will just be 16 possible values for m and n. So for case 9, that's also 16. So nice, we have almost finished our question. We're just almost there. Okay, so moving to our last case, when y is equal to 0 and z is equal to 0, we know that r, m, and n cannot be equal to 5 or 7. So each of them will be a value in this set. So now we'll continue to use prime factors to analyze the total number of combinations we can have. So for simplicity, let's just pick 3. Over here, there's one factor of 3, one factor of 3, and there are 2 factors of 3. So at most, there can be 6 factors of 3, which is also 3 to the 6, and the minimum is 0. So now we have some so let's use so let's just let the variable w be equal to the number of factors of 3. Great. Now we have case 10.1. So 10.1 is when w is equal to 6. So if we want to have 6 factors of 3, we can only have 9, because 9 is equal to 3 squared. So we need to have 9 times 9 times 9, because it's the only way we can achieve r, m, and n having 6 factors of 3 with only 3 numbers. So then there's only one value of r, m, and n for case 10.1, and we have case 10.2 when w is equal to 5. Similarly, it means that because 5 is equal to 2 plus 2 plus 1, since we only have three numbers, rm and n, so the factor of 5 must be distributed to three numbers. So let's just say r and m are both equal to 9 squared. If r is equal to 3 squared, or 9, so there will be two factors of 3, same for m. So if we want n to have one factor of 3, it can either be 3 or 6. So we have two possible values. Now we have arrived at case 10.3 when w is equal to 4, meaning that there are 4 multiples of 3. Firstly, we can have 2 plus 2 plus 0, or we can have 1 plus 1 plus 2. There's no other way we can allocate the 4 factors. So when the first one, let's just let r is equal to 9, m is equal to 9. So n is equal to 2, 4, or 8, which is relatively simple. Now we can have r is equal to 9, m is equal to 3 or 6, n is equal to 3 or 6. However, there is a trap here. We can't just count the number of total values for r, m, and n, because there is a trap here. Think of it in this way. If we have r is equal to 9, m is equal to 3, and n is equal to 6, this is the same as 9 times 3 times 2 times 3, which is equal to 9 times 9 times 2, which is actually essentially the same as this case above. Hence, we have to check for all of the possible cases to avoid making a mistake. So all of the possible choices include 9 squared times 2, 9 squared times 4, 9 squared times 8. Then we have 9 times 3 times 3, 9 times 3 times 6, 9 times 6 times 6. But we notice that there are a few duplicates for this one and this one, because this is the same as 9 times 2 squared times 3 squared is equal to 9 times 4. So in total, there's actually only 4 values of r, m, and n here. Now we have case 10.4 when w is equal to 3. So we can have one of them is being equal to 9, and one of them is equal to 3 or 6, and the last one being equal to 2, 4, or 8. So essentially 2 plus 1 plus 1. Or we can also have 1 plus 1, 1 plus 1 plus 1. So in the first situation, we can have 9 times 3 times 2, 9 times 3 times 4, 9 times 3 times 8. Or we can replace it with 6, 9 times 6 times 2, 9 times 6 times 4, 9 times 6 times 8. And we also need to be very careful when checking for any duplicates. For example, this one is essentially the same as this one, and these two are equal. So we can just write it as 27 times 2, 27 times 2 squared, 27 times 2 cubed, or 27 times 2 to the 4th. Or in the second situation of 1 plus 1 plus 1, we can have something such as 3 times 3 times 3 times 3, or we can have 3 times 3 times 6, 3 times 6 times 6, 6 times 6 times 6, which equals to 27, 27 times 2, 27 times 2 squared, or 27 times 2 cubed. So when we combine these two lists of these two cases, we find out there's actually only 5 distinct scenarios, which are these 5. So when w is equal to 3, we'll only have 5 distinct solutions. Okay, and in this case, when w is equal to 2, there will be only 2 factors of 2. So either we can have 2 lots of 2 in the first number and no factors of 2 in the other two numbers. Or we can have one lot of 2 in the first one, one lot of 2 in the second, and no factors of 2 in the third one. So we can just analyze these type of numbers. So in the first situation, 1r is equal to 9, m or n is equal to 2, 4, or 8. And 2 is equal to 2 to the power of 1, 4 is equal to 2 to the power of 2, 8 is equal to 2 to the power of 3. So the minimum number of factors of 2 is 2. And at most, there will be 6 factors of 2 for the first case. However, in the second scenario, we can let 2 of r, m, and if 2 of r, m, and n is equal to 3 or 6, then the third of them is equal to 2, 4, and 6. So r, m, and n contains at least one factor of 2, which is 3 times 2. And at most, there's 5 factors of 2, which can be achieved by 6 times 6 times 8. So, instead of 2, after considering 1 plus 1 plus 0, it's actually minimum is 1. So with the minimum being 1 and the maximum being 6, and we can find that there will be 6 possible values of r and n in this case. Okay, so now we have our second last case when w is equal to 1. So 1 of r and m is equal to 3 or 6. And the other two of them will be equal to 2, 4, or 8. So r, m, and n can contain at most 7 factors of 2 when we have 6 times 8 times 8. And must contain at least 2 of them when we have 3 times 2 times 2. So in this scenario, every number from 2 to 7 inclusive is a possible combination of the number of factors of 2. So we have 6 possible values when w is equal to 1. Okay, now it's our last one. Case 10.7 when w is equal to 0. It means that none of r, m, and n can be equal to 3, 6, or 9. So each of them is, okay, that was a horrible writing. I'm sorry. I'll write it again. This means that each of them must be equal to 2, 4, or 8, or we can just think of it as 2 to the power of 2, 2 to the power of 3. So Rmn must be a power of 2, and there will be at least 3 multiples of 2, and at most 9. So that means there are 7 possible values for this. Okay, now we can count the number of values we have in the 10th case and add them up together. So we have 1 plus 2 plus 4 plus 5 plus 6 plus 6 plus 7. So we have 31 for case 10. Nice. Okay, I'm so proud of you for persevering through this hard question and listening to my explanation. So now we can finally add up all of these numbers, which leads to a result of 85. Okay, so now we're finally on our last question. So I hope you've taken your time to attempt this question. Okay, now let's start doing it together. For how many positive integers x does there exist in a rectangular prism P, Q, R, S, T, U, V, W, labeled as shown with PR equaling to 1,867, PQ equaling to 2,090, and PT equals to x? So in my diagram, I have labeled P, R, PV, and PT, and in addition, I have added the lengths and x, and I have also labeled my base, height, and width as A, B, and C. Okay, so recall that before we have learned the Pythagorean theorem. It's in a right angle triangle, if my lengths are A, B, and C, A squared plus B squared is equal to C squared. So in our rectangular prism, we can see that there's actually right angles, because all sides in a rectangular prism are made of rectangles. So when we have U, V, P, and Q, this is a right angle. So this is A and this is equal to C. So we can see that we have a right triangle here. Similarly, we can also draw a diagram for our base. So we have P, S, Q, R, and this is A, this is B, and the question gave us that PR is equal to 1,867. So with these diagrams in mind, we can construct our three equations. Firstly, A squared plus B squared is equal to 1,867 squared. A squared plus C squared, oops, that was an ugly plus. C squared is equal to 2,019 squared. And finally, B squared plus C squared is equal to X squared. So now we have a system of equations. Great. So when we see a lot of variables, we might have different ways to solve them. And it's totally fine if you solve them using different methods. And at last, personally, I found the most efficient method was to add all three of the equations together. So we have two terms of A squared. So we have 2A squared plus, and we also have 2 of the B squared. So 2B squared, and similarly we have 2 C squares on one hand, and we have that equaling to this sum right over here. So I'll write it over here as I'm running out of space. So the right hand side is equal to the left hand side. And notice that over here, 2 is a common factor, so we can take the 2 out. So this thing is equal to 2 times A squared plus B squared plus C squared. So we can write that in our equation over here. So we have 2 times A squared plus B squared plus C squared is equal to this expression. And now we can isolate this thing when we multiply each side by 1 over 2. So 2 times 1 over 2 is just 1. And this expression times 1 over 2 is just this expression divided by 2. Okay, now when we have arrived at this complex equation, you might be thinking, what can you do? Well, here's a simple method. So in our first equation, we know that A squared plus B squared is equal to this. Well, isn't that A squared plus B squared exactly the same as this one? So we can actually substitute in the value of 1,867 squared plus C squared is equal to this expression. Then we can just move this expression to the other side, so we can isolate C squared. So we have C squared is equal to the same fraction minus this. And you may recall from some simple fraction addition in the past, this thing is just equal to, if we want to add up fractional terms, we need to make sure that they have the same denominator. So we multiply this by 2, so that we have 2 of 1,867 squared that is also negative. So it's just equal to negative of 1,867 squared plus this plus x squared divided by 2. And we can perform the similar operation. For example, we can substitute A squared plus C squared as this one, and we can substitute B squared plus C squared with this expression. So after simplifying, we will arrive at this system of equations. Firstly, we have A squared is equal to this. So yeah, when I'm writing the answers, just feel free to pause this video so you can practice your skills of manipulating variables. as this is quite important. Great, now we have our system of equations. Recall that A, B, and C are all lengths of the prism. So we know that a length must be positive and it must be greater than 0. So all of these expressions, since A is greater than 0, we know that A squared is greater than 0. That's why since this expression is equal to A squared, this one must also be equal to 0. Similarly, B and C are also lengths, so all of these are greater than 0. So we can now simplify them. And yeah, 2 multiplied by 0 is also 0. So when we move the 2 to the other side, the equation is remains unchanged. So this is our system of equations. Oops. And now we can isolate x squared. So the first equation states that x squared is smaller than this. Then we have x squared greater than 2019. And similarly, it's greater than this one. So over here, we can do some analysis. We know that in these 3 equations, this one is the greatest, and x is smaller than the greatest expression, which makes sense. And after analyzing this, we know that this one is larger than this one. So when we write our net equation of inequalities, we have okay, and just an explanation for what I did over here. A quick explanation of what I have done here in case you did not understand. If we say that x is larger than 2 and x is also larger than 5, if we draw a number line, we can see that since x has to satisfy both of these requirements, the solution will be x is larger than 5 because we need to satisfy the most limiting condition. So now let's go back to our equation. So we can just plug this into our calculator. This is around 786.55. Oh, I left the x squared. Sorry about that. So we have 769 is smaller than or equal to x, which is greater than and x is smaller than or equal to this integer. So the total number of x possible values is just the upper bound minus the lower bound plus 1, which is equal to 1,981. So in conclusion, there are 1,981 such integers such as x. So this is our final question. Thank you so much for listening to my lesson. I really hope that you enjoyed because math is extremely fun. And if you have any questions or suggestions so that I can improve my teaching, please reach out to me or reach out to Math Club by replying to this post or messaging us on Instagram and Discord. Thank you so much. I look forward to seeing you next week. Have a nice weekend. Bye!